Hello everybody, this is Sahan Liosi and now I'm going to explain the solution for the assignment 1. In the first problem, you're asked to draw the one-line diagram and determine these parameters. The first thing that you need is to draw this one-line diagram. Well, it is really hard to work with a three-phase system, so it is much easier to convert this system to a single line diagram. So let's see what we have here. We have a three-phase generation unit, a three-phase transmission line, and three-phase load. It is easier for us to work with Y connection, so we prefer to convert this delta connected load to a Y connected load. For this sake, we can write 9 with the angle of 20 degrees divided by 3 to obtain the Y connected load value. As you can see here, we have shown that load with 3 with the angle of 20 degrees. And for the transmission line and the generation unit, we do not need to change anything. So for drawing the single line diagram for the phase A, we can write the phase voltage as 120 with a degree of 0, and the transmission line impedance and the load impedance can be written in this format that we had calculated. So after that, we can calculate each of the requested parameters. In part A, you're asked to find the line-to-line voltage at the load side. Be careful that it is asked to calculate the line-to-line voltage and at the load side, because some of you have just calculated the voltage at the generation side and some of you have just calculated the load voltage, the phase voltage at the load side. So be careful that what are you asked exactly. Okay, we're going to use this diagram here. The load side voltage would be the voltage over this impedance. So we have two solutions for part A. We can obtain the current through this circuit and after that calculate the voltage over this impedance. Or the other method is that we know that there are two impedances here, the transmission line impedance and the load impedance. So we can use a simple voltage division here. For this sake, we can write the total voltage or the voltage from the source multiplied by the load impedance divided by the summation of all the impedances in the circuit, which is 2 plus J2 and 3 with the angle of 20 degrees. So as you can see here, the voltage over the load has been calculated here for phase A, phase B, and phase C. Just note that this value that has been written here is just for phase A. So if you want to do the same thing for phase B or phase C, you need to change this voltage. So for phase B, we have 120 volts with the angle of negative 120 degrees, and for phase C, this value is 120 volt with the 120 degrees phase shift. Okay, for part B, we are asked to calculate phase voltage at the load side. The point is that in delta connection, the phase and load voltages are the same. But what we have calculated here is the voltage for this circuit, or in other words, if you remember, we had converted this load impedance into Y connection load impedance. So the voltage that we have obtained here is actually for Y connection, not delta connection. So if you want to find the phase voltage at the load side, you need to convert that uh, phase voltage to line voltage, or as you can see here, the line voltage for phase A, using the formula that you already know, you have to multiply the phase voltage by a square root of 3, and also you need to increase the uh, phase of that voltage by positive 30 degrees. Or the other method that you can use is that you can say, for example, line voltage, which is VAB, is equal to VA minus VB. And if you write this from these values here, you can see that the result would be the same. The same thing for VBC and VCA. In the next part, you are asked to calculate the line currents. Let's go to the next part. For line current, again, you can use the diagram that you already have sketched at the beginning of the solution, this diagram. You can just write a simple KVL and find the current. So the voltage must be divided by the line impedance and load impedance. The voltage was 120 volt with 0 degrees for phase A, and we had the line and load impedances. Again, we're using the value that we had calculated for Y connection. The same thing for phase B and phase C. But you have to uh, consider this 120 degrees phase shift for phase B and phase C. In the next part, you have to calculate current on each phase, again at the load side. At this part, you can use the formula, or as you can see here, the line current here, IA, is equal to IAB minus ICA. The same thing for the phase B and phase C. You can write, for example, IB here is IBC minus IAB, and the same thing for IC. You can calculate the currents from this, or easily use this formula to obtain these values. Since we have a balanced system, it is much easier to use this formula both for calculating the currents and the voltage. And in the next part, you're asked to calculate complex power delivered by the source. For this sake, we can easily find the complex power using the formula that we know for the single phase, which was VI conjugate, but since it is a three-phase voltage, it should be 3 times by VI conjugate. Just you have to note that this voltage and current must be the phase voltage and current, or equivalently you can write root square of 3 multiplied by line voltage multiplied by conjugate of line current. This formula is also true all the times, for both for Y connection and delta connection. Just be careful that you have to write both of the voltage and currents in their line to line values. Okay, it is just a simple replacement. So we have this voltage and the current, so you can easily calculate the source power. If you need to obtain the active power and reactive power, you can easily say this is the active power and this part is the reactive power. And then you need to calculate the consumed power by the line and the load. For a single line circuit, we knew that the power, actually the complex power, can be calculated by Z multiplied by I square, actually the amplitude of I square. But for a three-phase system, this should be multiplied by 3. So for load complex power, we can write 3 multiplied by load impedance multiplied by load current. Again, this value is the impedance that we had calculated for the Y connection. So when you're going to write the current, you have to use this current, which is for the Y connection. And it is clear that in the Y connection, the line current and the phase current are the same. Because, for example, here, if we have a Y connection, this line current is the same current that goes through the load. The same thing for the transmission line, we have the line impedance and the current, so easily we can also obtain the complex power consumed by the line. And since it is an ideal system, we should expect that the generated power is equal to the consumed power. So the power that we calculated for the source should be equal to the summation of these two powers. And finally, you are asked to obtain the power factor. Based on the definition, we know that the power factor is the cosine of the phase shift between voltage and current. So we just need to obtain this phase shift. As you can see here, it is 46.2 degrees. So we can easily write cosine of 46.2 degrees, which is 0.69. And since we have inductive load, or we have this negative value here, we know that this 0.69 is lagging. The other approach to find this power factor is also the other definition for power factor is P divided by S. We already have calculated P here and also S here. So the other approach is to divide 4294 by 6204, which gives the same value. Again, it is lagging.